Five. Oh, nice. Wait, there's nothing coming through this volume, right? Should be muted. All right. Nice. We finally got there, guys. Took us only 13 minutes. We got this. Anyway, hey everyone. Welcome to the DESN 2K crash course. I'm Alif. Um, so yeah. Um, Today we're just gonna be going through just a brief like overview of pretty much the entire content of the course in the first half of this session. Then we'll take a quick break. Then in the second half, I'll go through a couple of exam style questions, things that you might likely see in the final exam. Um, so the stuff I found, well, the exam questions that I'm going to do are sort of like inspired by past papers, which I've seen over the course of like 3 to 4 years, as well as like questions from like back in 2018. So yeah, there's a whole range of questions that may come up. But first, yeah, let's quickly go through um, the basics or like the content. By the way, at any point, if you guys want me to like elaborate or like go into more detail, just raise your hand, ask a question. Anyone on the live stream, I'll be keeping an eye on the chat as well. Just yeah, if anything isn't clear or you want me to elaborate, just ask questions. Hello. Uh, yeah, that was Joe there. Cool. Let's move. Let's go to the first chapter I wanted to cover, which is base conversion. Oh, this is tiny. Um, let's see. Can I zoom in? Good enough. All right. So, um, on the exam, there will be I every year I see like 1 or 2 questions that have to do with like converting between bases, converting between like decimal points, fractional numbers. Um, this might have been, I think this was covered in 2141, if I'm correct. Yeah. Wasn't large too much, wasn't too much covered in this course, but it is on the exam. So I'll just quickly go through the brief revision here. So um, the most common one is going from hex to binary and binary to hex. You, I, all the exams I've seen have at least one question on that. So it's an easy mark, right? So let's switch to, that's not it. All right. So um, when you convert to hex to decimal, also hex to binary, there are a couple ways of doing it. You could go through the long way, which is we can go through go hex to decimal, which should be pretty straightforward, and then decimal to binary, right? That's I can say that's like the standard way of doing it. Now, there is a shortcut, right? And this using the shortcut can actually save you a lot of time. Now, the thing with hex, how many, how big is like one digit of a hex number? It's in the name, right? It's 16. And how much is 16, or how many bits is 16 in binary? It's 4 bits, right? So the trick we can use is, let's give myself a bit of space here, is that we can actually split up each digit of hex into 4 binary bits. So let's say with this example, we look at the first bit. We have B, right? What's B in decimal? What's that? 11, right? 11. So all the trick is we just need to convert 11 into binary. So what's that? If you remember your binary, we have like I said, hex is 4 bits. So we have the 8-bit, the 4, the 2, and the 1. And to convert that, we just look at the highest bit. So let's say 8, and we just see if it fits within 11. Does 8 fit in 11? It does. So we put a 1 there. and then we do -8, and we keep what is this 4 in our head. Does 4 fit into 4? Wait, 11 minus 8 is not 4. You are, what am I doing? Is 11 minus 8 3? I can math. Don't worry, guys. I got you guys. Does 4 fit into 3? No, it doesn't. So we put a 0. Does 2 fit into 3? It does. And then we minus 2, and then we're left with 1. And obviously, well, 1 fits into 1, and then we're left with 0. So that's how we convert, well, like a decimal into binary. But that's only for one digit. And you can actually do this pretty fast. So this is, well, that's B, right? Now we'll do the same thing with E. So what's E in decimal? That's, what's it, 14? 14. So let's convert that into binary. So we have, what, 8, 1, 1, and what's that? That's 12, 1 to 14. So it's 1, 1, 1, 0. And we do that for each one. So E again is 1, 1, 1, 0. And then F, if you have enough practice, you can pretty much pull off your head, which is just all ones, right? Yeah, and that's the end result. That is beef in binary. Now, we can actually do it the other way around. Let me give myself a lot of space here. That is not it. Put that down. Cool. So with binary, if you're asked to convert into hex, we do the exact same thing, but the other way around. So notice when we converted from hex to binary, we split up into 4 bits. Now, to go from binary to hex, we also split up into 4 bits. This question has nicely like given it up for us. So we have like each bit's already, well, nicely split up. Oops. So now all we need to do is just look at each 4 bits from right to left and determine what hex value that is. So for example, these 4 bits, right? That's 0101. Quickly convert that into decimal. What is that? 1 plus 5, right? Sorry, 1 plus 4, which is 5. Does everyone know how I got there? How I just immediately got 5 from this number? Wait, it is 5, right? Just want to do a sanity check. I'm not tripping because, yeah, I've already done, well, 11 minus 8 equals 4, which is not ideal. So yeah, so first digit is 5. Then we have this second one. What is that? That is just 2, right? This one is 2. This third set, well, that's just all zeros. So you just do 0. And then this last set is another 2. So in hex, we actually get 2025 as the final answer. So yeah, so if you're converting from binary to hex, split it up. So yeah, that's just some straightforward, should have been 2-on-4 and stuff. Let's look at a little bit more. Look at this now. All right. So now we have like a few, couple other number systems. When we're dealing with signed numbers, there are actually a couple ways we can represent them in binary, right? So first of all, we have unsigned, which is not signed at all. But then there's 3 others. We have signed magnitude. What is this doing here? We have signed magnitude, which is basically the leftmost bit represents whether or not the number is negative or not. So for example, let's just suppose I had like this random number. All we need to do is look at this bit. If that bit is a 1, it's a negative. If it's 0, it's positive. And then this number here, oh, where is it? This number here stays the same. So like whatever representation of binary it is, you just read it as that, right? And then you just append well, a positive or a negative symbol at the front. Ones complement, on the other hand, is when we have a number. Let's say, for example, let's do a 4-bit example. Let's say we have 0, 1, 1, 0. All right. The ones complement basically means just to flip it around, or like you XOR it with itself. Yeah. Um. So ones complement, this would be 1, 0, 0, 1. And the way you can check if it's negative, if just by looking at it, is by noticing um the most significant bit, which again, similar to sign magnitude, we check, you can see if it's negative. If it's negative, then that bit will be a 1. And with 2's complement, it's similar, but instead of just flipping it, we also add a 1. We add 1 to the result. So you would um, add 1 here. Let's move this away. So you would add 1, and with binary addition, that will be 0, carry the 1. And that would be what? That will be the 2's complement version of 0, 1, 1, 0. All right. So let's do the example question, which is 0xd6. All right. That's in hex. So our first task is to first convert it into binary. All right. So let's do the same thing we did before, which is we split it up. So we have D and we have 6. All right. What's D in binary? Anyone want to guess? I heard it's 0, 1, 0, 1. 1, 0, 1, 0. Yes. Cool. And what's 6? 0, 1, 1, 0. Yeah. Cool. So this is our unsigned representation of the binary version. And all we need to do now is just convert this into, well, this question isn't really that good, but the idea was to convert it back into decimal. So in decimal, this would be 1101. You are right. Cool. Yeah, I can do math. This right. Where was I? Yeah. So we want to convert this into decimal. And the way we can do that is just do, well, actually the easiest way of to do this is actually just convert it straight from hex. Um, so let's pull up a calculator. So all we do here is we just do, what's D? D is 14, right? So it's 14 times 6 plus 6. And that would be 214. So D6 into unsigned is 214. Now, F is 15, you are right. I am, yeah, and I think that should still be 214. Hold on. Let's see. So let's do 13 times 6 plus 6. Yeah, it is 214. Yeah, so just double check that I've done my math correct, because my mental math is not good. Yeah, that is helpful. Cool. Right. Now with sign magnitude, all we do is we just take so we have a binary representation already, which is 1, 0, 1, 0, 1, 1, 0. And all we do is we just look at this section of the number, because with sign magnitude, all this does is just represent whether or not it is positive or negative. So converting this, if we just take a shortcut and I just look at the answer, uh, the we actually get this is equal to uh, negative 86, because this section, or these set of bits represent 86, and since this is a 1, we put a negative sign in the front. Cool. Oh, hold on. Yeah. Now, with 1's complement, all we do is we just flip the bits. So instead of we have 1 1 0 1, we go 0 0 1 0 and 1 0 0 1. And this, if you convert this into decimal, what we end up getting is we end up getting 41, right? So that means the original number would have been negative 41, because when we because we saw that the first bit was a 1, which means we knew it was negative, which is why we had to flip it to get the original number. If, for example, we saw that bit was actually a 0, then we wouldn't need to flip it since it's already in a positive form. All right, now for the hard one, we have the 2's complement. 2's complement, all we do is just add 1 to the 1's complement. So with 1's complement, we had this. So let's just add 1 to it. So that and add 1. So 1 plus 1, that's 0, carry the 1. 1 plus 0 is 1, and then everything else should just follow through. Yep. And then this number is, whatever this number is the, well, the negative representation of what we had. So let's just convert that into decimal, and we should get, yep, 42. So that means our original number was negative 42. So yeah, so D6 into unsigned was 214. D6 into signed was negative 86. Then we had negative 41 and negative 42. Okay, cool. As okay, with bases other than binary and hex, there's a neat little trick where sorry, there's a neat little trick where all we do is we just, if it's from another base to 10, it's simple. All we do is just multiply each digit by the power of the base. So in this case, let's start from the right side. Each digit represents the nth power. So what does that mean? For example, the first digit would be, where's my pen? Would be 7 power of 0. Second would be 7 power of 1. That would be 7 power of 2. And all we do is we just multiply our way through. So if we multiply this, thanks for the calculator, you have that 49 times 3 plus 7 times 5 plus 2. And yep, that looks about right. We have 184 in base 10. Now, if we want to convert it the other way around, what we do is, sorry, I've lost my voice, is, sorry, is, let's this. What we do is we keep dividing by the base, and we take the remainder. So what's 184 divided by 7? That is 26. So we divide by 7. We get 26. Remainder 2, right? Then what we do is we take this 26 and we divide it again. 26 divided by 7. should be 3 remainder 4. Wait, I can count. Don't worry about it. And then what we have left, we have 3. 3 divided by 7, well, that's just the remainder 3. And now, if you notice the remainders, this actually gives us our original number, but we have to read it from the top down. So from the bottom up, sorry. So we read it this way. Oops. And we can see we have 3, 5, 2. So our final answer would be 3, 5, 2. And that's our original number. Oh, yeah. Cool. There's also, hold on, I don't have a example question for this. I was supposed to include it. But if we are asked to include decimals, so let's say, for example, we have 352 point, what's your favorite number? 67, sure. Wait, you can't have 7 in base 7. The next closest thing is 6. Why not? All right. Okay, I can put a little 7 there, so it looks like a 6, 7. It's close enough. Anyway, so if we convert this into base 10, we actually do a similar thing. So we had 7, so this is 7 power of 2, 7 power of 1, and then the decimals are actually the negative powers. So what you would do is you would end up multiplying this by 1 over 7, and you multiply this by 1 over 49, and you just sum them up to get your base 10 representation. And it's a similar thing to go towards to go through decimal to base 7 as well, except we multiply out through the quotient, well, the fractional parts. Yeah. Anyway, that was much longer than I wanted to spend on base conversion. Let's actually go through some of the actual 2142 content, or DESN2K. Right. So let's first talk about the ARM TTI architecture. So ARM, or at least our processor, is something called a reduced instruction set computer. Right. So what does this mean? So if you compare it to, say, hold on, to other systems, some of them have a bit more. I think it was another one was 6, but this is not really. We don't really study this, but for reference, other systems might use something called a complex instruction set computer, such as, say, like x86 or Intel, right? They would use something called CISC. ARM uses something called RISC. What that basically means is that our instruction sets are reduced. Well, we don't have as many instruction sets to build. So what does that mean, like, for the manufacturers? It makes it easier to sort of make and manufacture the CPU. Because if you think about it, each instruction has a dedicated circuit, right? So if we think about, like, this is our CPU, right? We have to think about what we can fit inside there. So we could say, like, we want we have our ALU. Oh, hold on. We have, like, our ALU here. We also have, like, say, like, buses into memory, right? And then we might have, like, some IO stuff. And there's a lot of things that we could include in a CPU. With RISC, we want to minimize that. So what's the trade-off between minimizing it? Well, it sort of puts more effort onto us programmers. So if you think about what we've done if you guys recall lab 4, we had, when we want to control an LED, we use something called memory mapped I/O, right? If you guys recall. Now, what an alternative thing could be was some architectures have dedicated instructions to control um, output. So they might have like another, like say another bus here. Oh, I've already drawn it, but they would have had another bus. They go straight into like some interface that deals with I/O, and there's a specific instruction for that. And for people programming in, like say x86, it makes their life easy for them. They can just run like a certain instruction to deal with certain inputs and outputs. Whereas for us, we have to use something called memory mapped I/O, right? So that's the difference between RISC and CISC. It's the trade-off between it's good for like manufacturing. Here it's for CISC, it's more good for programmers or like developers because they have more to work with. So yeah, which is why you notice with RISC processors, they tend to use in like embedded systems because we want to try save cost as much as possible. Whereas compared to say your laptops, you're probably running some form of like Intel processor where you want to get the most power out of it, or like more processing power out of it, right? Cool. Let's move on to fetch. Hold on. Yep. So the next step I want to talk about was the fetch, decode, execute cycle. So what is it? Um, it's basically the pipeline in which our processor runs in. So let's think about how this works. So let's assume this is our memory, okay? And let's say this is our CPU. And inside our memory, we have instructions. Let's say we have an add instruction in there, okay? So what needs to happen is the system needs to take this add instruction and feed it into the CPU, right? Now, thing is, the CPU doesn't quite understand what add is yet, right? Because the CPU is essentially just it's just a circuit. What we need to do is sort of decode it first. So there is a circuit between the memory and the actual ALU, or I can write this as ALU, which sort of decodes this um this instruction and tells it like what should do. So let's say I don't know that tells you to do 1 plus 1, and only then can the CPU understand what to do. So okay, now I can actually see 1 plus 1. Let's turn that into 2, and then that goes out into wherever. Now, obviously, as you can see, this takes time. You have to move it from memory, you have to decode it, and then you have to actually execute it. And now this leads us to the pipeline. So as let's say for example, okay, we had an add instruction here. Let's say we have a sub instruction and we have a move instruction. So what happens here? So first step, we take the add instruction and we move it to the decoder. Right. Now, on the next clock cycle, what happens is the decoder decodes it into an instruction. And then as it's decoding, the next instruction is being moved to the decoder. Then on the next clock cycle, the instruction is actually executed into the CPU. And whilst that's being executed, the decoder decodes this instruction. And let's say that, I don't know, 2 minus 1. And then as that's being decoded, the next instruction is being moved into the system. And then you might have seen this very famous graph of the pipeline. So we have our say this instruction. So first we fetch our instruction, then we decode it, and then we execute. But whilst this is decoding, the second instruction is being fetched. Oops, I can draw. And as the second instruction is being decoded, the first instruction is being executed, and the third instruction is being fetched. And this sort of just runs all the time. And which is why when we say when we use the fetch execute cycle, so fetch decode execute cycle, we can say that we're actually running it at almost 3 times a normal speed, which is the main advantage as to why we do something like this. Cool. Let's move on to CPSR flags. Anyway, any questions so far? Anything on chat? 13. Oh yeah, yeah. I don't worry, guys. I swear I can do math. I'm just um not mathing right now. Cool. Uh, let's talk about the CPSR. So what was the CPSR, right? Um, the CPSR is essentially just like a big register. Also, it's just a normal. It's a 32-bit register, but inside this register, there are certain bits that correspond to certain flags, and you might have come across this already. You got the carry flag, you got the zero flag, the negative flag, and the overflow flag. All right. Now, what do each of these do? Carry, well, that just represents the carry bit. Z, well, that's the 0 bit. Let's move this. We have N, which is negative, and then we have V, which is overflow. Now, the thing about this, right, is, well, this is pretty much self-explanatory, but what tends to catch people off guard is when they are actually like changed and what like the scenario in which these flags are updated. So let's talk about how they're actually updated, right? So okay, let's start with the most obvious one, 0, right? So hold on, let me take a step back real quick. So the CPSR flags are updated when we do some sort of comparison, correct? Right? Now that comparison usually is if we use say the CMP instruction, it's like we we take this difference between A1 like we take a difference between two numbers, right? Now, if the result of these two numbers being subtracted is what updates the flag. So 0, that's the most obvious one. That implies that the result of the subtraction is just 0. All right, pretty straightforward. The next one is negative. All that does is checks if the 31st bit, or like the leftmost bit, is a 1 or not. All right. So in other words, is it negative? Because remember, as we saw in the base conversion chapter, the leftmost bit just determines if a signed number is negative or not. Right. So that just basically means the MSB is 1, which means it's negative. Now, the thing that people get confused with is carry and overflow. So with carry, what happens is essentially when we do a negative sorry, when we subtract two numbers, you know how we can usually carry bits around. So let's say, for example, what's a good example here? I want to do 12 minus let's say 11. Oh, let's say 12 minus 6. 6 is a good number. Why not? Right? When I want to subtract 2, like 6 from 2, I can't quite do that, right? I need to borrow a bit from the next digit. Now, the same thing happens. That's essentially what we're trying to check. Is does the end result have any borrowing? So that means, say, if the last digit is smaller. Sorry, let's say if you think of A1, A2, we have let's say we have like one. Oh my god, where's my pen? We have like 1, 2, 3, 4. We have 2, 4, 6, 8. All we want to check is does this last subtraction need to carry or like need to borrow from anything? So checks checks if there is borrow. Right? Now, overflow is where things get a little bit confusing. Because a lot of people sort of like interchange the definition of overflow and carry. They think it's like overflow is when you lose a bit, or like when you say like you lose a bit to the left, like it overflows, right? Something like let's say something like this, 1, 1, 1. When you plus 1, you obviously get like all zeros, right? Uh, that's what most people think it is, which it is technically overflow, but that is not how the overflow flag is actually calculated. The way it works is it actually checks whether or not the carry of it checks if the carry coming in is equal to the carry going out. Now that's a little bit confusing, right? But let's follow an example. Let's say, for example, we have 1, 1, 1, 0, 1 plus see 1, 1. This is add these two numbers together. Hold on. No, let's not add those two numbers together. Let's do 0, 1, 1. Okay, let's do this. So obviously, as you can see, this number would lead us to, if we add them together, something like that, right? If we're using unsigned, this is not a problem. But as soon as you think of this as a signed number, what do you notice? We've gone from two positive numbers into a negative number. And that's what overflow is trying to detect. So what we mean by carry in versus carry out is we look at this last sorry, this last placement, last digits. So what's the carry going into these last digits? So as we did this addition, so let's say 1 plus 1, that is a 0. Then we carry, right? Then we have 1 plus 0 plus 1. That's another, that's 1 plus 1, which is 10. 1, 0, so we put a 0, and we carry. Then what's 1 plus 1 plus 0? That's another 10 or 0. And then we have this. So we have 0 plus 0 plus the carry bit, which is 1. Now, the carry going into this digits is 1, right? From the previous, we have a carry bit here. But what's the carry going out of this number? There is no carry, right? The carry here is 0. So we're actually comparing these two numbers. And that's what detects overflow. So that's just so yeah, a lot of people tend to confuse what C and V are, and that's sort of like the way it works. Carry is literally just whether or not so there's an extra digit that's needed, whereas an overflow checks if the sign changes when it's not supposed to, and we do that by comparing the carry bits. Cool. What is this? Right. For this computation, we can do this. So let's say, so for this, is there any carry bit? So the carry bit is literally just the last bit that comes out. So in this case, the carry bit here is 0, right? So we would have C equals 0. Now, the 0 bit is checks if all the bits are 0. So, oops. And as you can see, well, this obviously isn't all 0. So the 0 flag is 0. Now the N just checks the most significant bit, right? What's the most significant bit here? 1. So N, in this case, is 1. And then the overflow flag, well, we compare the carry in coming to the carry out. So that is this compared to this bit here, which is, well, it's hard to see. We're comparing is 0 equal to 1. And it isn't. So therefore, the overflow flag would be, oops, that's not the right pen. The overflow flag would be 1. Oh, I should probably make a correction. This should be not equals to. Yep. So for this computation, if you were to run, like, say, add s, and on these two numbers, you would get these flags. Oh, yes. Sorry, carry in basically means the carry from the last well, on the last digit. So when we did this calculation, say like we did 1 plus 1, sorry, we had 1 plus 1 plus 0, right? And that gives us 10, correct? So we put a 0 here, and then we have this carry. You have a carry on this last on the last digits. Now when we do this last computation, 0 plus 0, that's 0, plus the carry bit, which is 1, we get 1, correct? So, but we have 1 without a carry. So the carry bit carry out would be 0, but the carry in is 1. It just means the carry for the last computation. That's what carry in is. Yes? It just checks if it needs to borrow. So if say, for example, you had a smaller number on the top and a bigger number at the bottom, you would obviously need to borrow a digit, right? Yeah, from the next one. So if you're already at the end digit, obviously you need to borrow from somewhere, right? So that's what that carry flag sort of represents. Like, it just grabs an imaginary, it pulls out an imaginary 1. And if you have to do that, then the carry flag will get updated. And for addition, it's, well, if it overflows, or like if number doesn't fit inside the result, then that's when the 1 comes over. Was that a hand there? Yep. Yep. So if you think about it, if you add two positive numbers together, you would expect a positive number, right? But if it ends up being negative, then it's an overflow. And same thing, if you have two negative numbers and you add them together, you would still expect a negative number. But if for some reason you end up with a positive number, then that means an overflow has occurred. Any other questions? Stream looks all right. Cool. Oh, we are not in time. Okay. I'm just going to quickly go through this. So when do these CPSR flags updates? There's actually there are three ways of doing this, right? We can either use the compare functions, right? So you've done your, like, in your labs, you have done, like, CMP R1, something like that. But you can also use your S flags. So that would be like something like, say, like your add S R0, I don't know, let's say something like that. this would update your carry flag based on the result. There's also one more that people tend to miss quite a lot, which is your shifter. So your shifter can also update your carry flag. So let's say with a move function, you have your say R0, R1, and then you also have your barrel shifter, right? If you guys would call the barrel shifter, where you shift the result by a couple bits. So let's say your left shift, something like that. Now, if something like this can also update your carry flags, also your CPSR flags, my bad, which is people tend to like miss that quite a lot in some exam questions, because I have seen quite a few questions where they ask about like updating your flags, and a lot of people, these two people tend to get correct, but they tend to miss this one. So yeah, just bear in mind that you can also update your flags by using your shifter. Cool. Is there anything else? Yep. So I've got a quick question here. So with CMP, there's also like a couple other variations of CMP. You might have seen them. You've got like PST. You've got PEQ. Now all these do is do different variations of um of different variations of instruction. So with CMP, CMP does like R0, R1 minus R0, right? And compares that result. PST, I believe, does AND. So it does AND R1, R0. So this is actually equivalent to AND S. And this would be, and CMP would be equivalent. Hold on, let's clear up some space. So CMP is actually equivalent to sub S, right? And something like PST is equivalent to AND S. Now, can anyone take a guess as to why we even have the CMP and PST instructions in the first place? Like, why can't we just use sub S and AND S? Yep. Yeah, exactly. If you want to compare the results, and you don't want to save the result, if we didn't have CMP, we'd have to store, like, if we want to use sub S, we'd have to store that result somewhere. But with CMP, we can just straight away discard it. And that's important because, say with like bigger programs, right? We only have like 15 registers available for us, right? And well, registers, like, they're a precious resource, and they might be like, we might have a use case for each of them. So if you don't want to like discard, if you don't want to keep it, we have to put it somewhere. Sub S suddenly becomes a problem for us because we're out of registers. Yeah. But say like with other systems, let's say if you guys remember MIPS, if you have done 1521, you would have had like a 0 register. That's sort of like a trash register we can dump anything into. ARM doesn't have that, which is why we have these instructions that just sort of dump the result for us. Cool. Yep. And following from the CPSR flags, we also have the conditional executions. So all that does is, when we have, let's say, an instruction, we can add like a suffix to it that determines whether or not that instruction should run. Let's say, for example, we have LE, which sort of asks if we should only execute this if the result was less than or equal to. And we can do that and the way this works is by comparing our CPSR flags. For example, the carry bit, right? When we compare, because when we compare, we subtract two numbers. If, say, for example, A2, sorry, if A2 was bigger than A1, then obviously A2 is bigger. Oh, sorry, that means our carry flag would be 1, which suggests that every time carry flag is 1, it means the unsigned value of A1 and A2 means A2 must be bigger than A1. That was a really weird way of putting it. But yeah, you can check each of these flags. Oh, sorry, combinations of these flags can tell you different like relationships between numbers, and you can see that on your data sheet, which you should have in the exam. Yeah. Let's and yeah, you can. The most important thing you want to do with this is obviously like branching. So you can do like you've got your BLEs, your BGTs, um, that you would have used in the labs. And speaking of that, let's go to branching. All right. So branching. That's sort of we know what branching is. It's when we move to different places in your program. The one thing I do want to since we are short on time. Okay. Um, the one thing I want to talk about branching is the main disadvantage, right? So if you think back to the fetch, decode, execute cycle, right? We sort of we load the upcoming instructions as we go along, right? Now, what happens if suddenly we branch? What ends up happening is what am I doing? Um, what ends up happening is when we branch. Let's say we branch at this location here, right? So suddenly we move to a different place in the program. What happens to these ones here that we've sort of prepared? We have to discard them, right? So this is something called flushing the pipeline, right? So when we branch, we have to flush the pipeline. That means we basically clear out whatever was in the fetch, decode, execute cycle, and that means we also have to start again. We have to start filling it up, right? So I've got a quick example here. So let's say, for example, when we start the program, let's see. So when we first start, this gets fetched, right? We fetch that. Then after that, this gets decoded, and then this line gets fetched, right? And then as this gets executed, this gets decoded, and this line gets fetched. Right? That's how the fetch, decode, execute cycle works. Now, what happens when we're on line 5, right? So let's say we are executing this line, right? While we're executing, this line is being decoded, and this line is being fetched, right? You see that? But as soon as this line executes, we suddenly jump to here. And now these two lines right now are useless to us because it's not the right order anymore. So what ends up happening is we have to clear the entire pipeline. So now the pipeline's empty. And then we start again. So we have to fetch this instruction. Then we decode this instruction. And then we fetch the next one. And then after that, only then do we execute and then decode, then fetch. And then as soon as we hit this line here, let's say we're back to executing this line, and then we have our decode and fetch on some imaginary lines here. What ends up happening? This gets flushed again, because technically moving our PC counts as a branch. So this gets flushed, and then we move back to wherever the LR points us to. And that's the main reason why, if possible, we want to avoid branches. So if you see like a question that asks, let's say, write this program and keep it optimal, the idea is we want to try avoid branches. And how do we avoid branches? We can use conditional statements, right? Cool. All right. So this is this is another disadvantage I want to talk about with branching. So I pulled this off from the well, the R manual. Like there's a big R manual, and we have this table here, and it sort of shows you how an instruction is formatted. So with the branch statement, this is sort of the the opcode for branch, which is 101, and then we have the L bit, which basically means you want to link. So if you remember your B, your branch, and then your BL, which is your branch and link. So this bit here determines if whether or not we want to enable the link. And then we also have our conditional statements at the start, like your GT, your BE or whatever. Now, if you notice this large part here, right? We've got 23 bits to play with. So the way that the branch works is you branch to like it sort of jumps. It's like a PC relative instruction. You can jump to a certain address based off your PC, right? So it's an offset. Now, you can see the problem with this, right? Um, with this, we only have 24 bits, right? So 24 bits to play with. Oh, sorry, 23 bits to play with, right? And if you actually look into the data sheet, it says the maximum size we can jump is actually 32 megabytes, right? So if you calculate this, we have 2 to the power of 23, which is, let's see, that divided by, hold on, 2 to the power of 23, and let's convert that into, this ends up being 8 megabytes. Oh, well, that doesn't make sense. Why do you think the data sheet says we have 32 megabytes, but when we do the math, we have 23 bits? It's only giving us 8. Anyone want to take a guess as to why? Sorry? The memory does start at OX4, you're correct. But we want to think about, we can actually technically branch to anywhere, right? So I think the most, the most likely place you want to branch to is within, like, well, not within the memory, but within the actual flash memory. So that'll be like, your 0x00, well, the first, what is it, couple, I forgot how long, but it's like a first couple kilobytes at the top. So it's not quite to do with where the memory is located. And I don't know, take another guess. Think about instructions. How big are instructions? Exactly. We can instructions are, well, someone answered, we can shift. We can do the shift because instructions have to be aligned with the word boundary, right? If you guys remember the boundaries, so that means they have to be aligned on, like, oops, they have to be aligned on 4 byte boundaries, right? So you can't have an instruction on, like, say, 0x, like 001, like this is illegal, right? Because that's not aligned with a 4 byte boundary. So what does that mean? It means that our instructions, we can never have what's called instruction as offset that isn't a multiple of 4, right? So instead of just having 2 useless bits at the end, because if it's a multiple of 4, it means the last 2 bits must be a 0. So the way to enforce this is by completely excluding those last 2 bits. So if you think about it like this, we have like, oh my god, let's say we have a bunch of binary, and then at the very end, we must have a 0, 0 at the end to make it a multiple of 4, right? Now, the way we do this is instead we just omit this altogether, like we just get rid of that, and then we just shift this by 2, right? So we shift it by 2 bytes over, so that gives us the 2 missing, it enforces that our boundary is at a 4-byte boundary, and it also allows us to extend our range up from 8 megabytes. If we shift this by 2, that ends up being, what's that, 8 times 2 times 2, and that actually gives us our 32 megabyte limit. Cool. So yeah, just to recap, two disadvantages of using branch. One is it flushes our pipeline, right? And that's obvious, that reduces the time taken. So in a way, you can say a branch statement takes 3 clock cycles to execute, because we need to flush it, then we need to restart our fetch, restart our decode, and then only can we execute, right? And then the other advantage, or the disadvantage, is the range at which we can branch, which is only 32 megabytes. Cool. One thing I also want to talk about, which might come up, is the jump tables. So your jump table is basically when, let's say we have this sort of C code, right? Which is a switch statement. Are you guys familiar with switch statements? All right, that's all right. So essentially, a switch statement is, you guys know your if and else's, right? So a switch statement is basically a bunch of if and else's. So we have something like that, right? So what this switch statement basically could translate to is, we first check is this variable equal to the case. So it will look something like, if x is equal to 0, then do something. Then if x is equal to 1, then do something. Then if x is equal to 2, then do something. And then you have, obviously you have your final else, which does whenever everything else is at run. So let's say in this case we have default is equal to that statement there. So we have y is equal to the question mark. So that's what a switch statement sort of looks like in C. Now, there's actually a way to do this with well, let's say, sorry, let me restart. If we wanted to implement this in assembly, which actually, let's move to a text editor. I think I should have a text editor up here. Okay. This is, there's no VS Code here, so we'll have to make do. Okay, so we had so let's say we want to implement your switch case, right? So we had like, if x is equal to 0, then do something. Then else if x is equal to 1, do something else, right? And then let's just say we had our else statement here. So let's implement this, right? So how do we do this in assembly? So the way we can do this is something called a jump table. So if you remember your labels, let's say we have a bunch of cases, right? Let's label this case 1, case 2, case 3, and then we have like our else when nothing else runs. Okay. What does it let me use else? There you go. It's a very misspelled else. Right. So these are our labels. And if you remember with branches, we can branch to these labels. And what we can do is actually make something called a jump table. So a jump table is essentially, so here's a label. We can define BCD. Oops. something like this. So you guys remember, what does DCD do? It stores a word, right? And what are these? These are labels. And these also store the addresses, right? And how big is an address? It's a word. Yep, 32-bit, which is a word. Um, Now, what we can do now is do a little trick called, so let's say first we want to load, hold on, let's say we have our main here. Let's do this. We can do, we can load the jump table address into R0. So what does this do? R0 now looks at this whatever is in jump table, which in this case is the address of case 1, right? Now, what we can do is we can do something called, we can do a bit of offsetting. So if you remember, when we load, we can offset, uh, the value by a certain amount. Let's say we want to do case 2, right? If we want to do case 2, we can offset it by, well, how much do we need to offset from case 1 to case 2? You guys know? How many bytes does it take to go from one DCD to a next DCD? 4 bytes, right? So we can do something like this. Oh, syntax is not very happy because this is not an ARM compiler, but we're trying our best. So yeah, so if we want to go to case 2, we can do something like this. So we move the PC into the address of R0 plus 4, which is case 2. So it's saying, let's go to case 2. So let's say I have an instruction here. What was it? Move, let's just say A1. Let's just say A2 is equal to B, was it B? Something like that, right? Hold on. Why can't I scroll down? There's no scrolling on this? Okay, that's cool. Oh, okay. Yeah, that'll have to do. Okay, anyway. So yeah, now, but obviously we don't want to hard code it to 4. So what can we do? Let's suppose, if you remember in our, let's see, on here, we have int x, right? So let's just suppose int x goes to, let's just say int x a1 and y is a2, all right? Just for the sake of this example program. So if you go back, let's just say like a1 is given to us already, all right? So do a1, oh, there's no comments. That's great. And then a2 is y, right? So what we can do is, instead of jumping from R0 to 4, what we can do is you do A1, but A1 was just a number. But to jump between words, we need to jump 4 bytes, right? So how do we make sure that A1 is a multiple of 4? What we can do is we can actually just times it by, just left shift it by 2. So what this does, it shifts A1, which is like a number from like 1 to 3, left shifts it by 2, which times it by 4, which then corresponds to our different cases in the jump table. Yeah. And there's also one more edge case that we need to think about, which is your else statement. So we know that x goes from 0 to 3. Yeah, so 0 to 2. So what we can do is we can just do a simple compare. We can do a1, let's compare it with 2, right? So that means if a1 is, we just want to compare it with the maximum amount that our jump table can take, because we have 3 separate cases. We have 0, 1, and 2. All right. So if someone inputs a number bigger than that, what we can do is we can jump straight to the end. So we can do something like B, let's see, HI, and we can go to our else statement, which see if I can like that. And let's just say what was the else statement? Say move A to my example program had question mark. So we set Y to become a question mark. And just we can also like just fill in the rest. So after each case, let's hold on. Let's add one more thing. Let's have an exit thing, and let's just have a no op there. So after each case, all we can do is just branch to exit. Yeah, and we can just do something like this, and this should be the assembly equivalent of our C program that we had over here. Yeah, so you can see when x is 0, we want A. If x is 1, we want B. And if x is 2, we want C. If else, we want Y to be a question mark. And that is what we've got going on here. Does that make sense to everyone? I feel like it was kind of rushed. Yes? Yep. And that leads us to the next part, which is the disadvantage of a jump table. So here, obviously, an alternative you could do is have like a bunch of, say, like, you compare A1 to, say, 0. And if it's equal, then you can branch to case 0 or case 1, sorry. Then you can do like C, compare A1 with 1, and then you can do your next like branch of equal. But obviously, you can see that the issue with this is you'll end up having lots of compare statements, right? The branch tables, you only need you don't even need it. Well, you need one compare, and then you just jump straight there. But then that leads to the um, the disadvantage. Let's say, for example, we had a case where, so we had our if, we had our ifs, right? And then let's say we had another case where if x was equal to 7, or let's give something even like 4,000, right? Then we can do y is equal to, I don't know, something else, right? And then I had a bunch of else ifs, right? Now, if we had something like this, we would need a case for each jump table, which means if we wanted to implement this, we would have like a case 1, case 2, case 3, and then, oh my god, this is a. Can you guys see this? If it's small, like, how do we? If I zoom in, I can't. Okay, you know what? Oh, this works. All right. Um, so if we had like a case like 4,000, all we need to do is have like a bunch of empty cases like this, all the way up to how many? All the way up to our maximum case, which, as you can tell, is an issue. So you sort of have to find, like, you have to like sort of determine whether or not a jump table is suitable for your application. So like if your cases are what's called condensed, or like the dense. So let's say like you have like each case is next to each other. So in our example, we had 1, 2, and 3. They're all next to each other. That's a good case I'm using a jump table. Now, if you had like say another case which is like far away, let's say 4,000, then obviously that's not a good case for the jump table. In which case, if you had like if you had some like far cases, the best or the best approach would be to just use a bunch of branching, like a bunch of compares and branchings, which in of itself is also has more of a big disadvantage. Cool. Any questions? Sorry, I thought that was a bit fast. Um, let's see. Um, I'm going to quickly go through this first because I think there's a couple questions that people get caught up on this one. Oh, this is already filled in. Um, let's okay. Now let's talk about like memory layout real quick. All right. So with memory, there are a couple of ways we can define like our data section. We have our we have DCD, we have DCW, and we have DCB, right? So DCD means the word, which is how many bytes? Oh, sorry, how many bits? 32. Nice. Then DCW, which is half word. How many bits is a half word? I heard 16. And then we also have our byte, which is 8 bits, right? So we have 32 bits, 16 bits, and 8 bits. And this also corresponds to 4 bytes, 2 bytes, and 1 byte. All right. Now, when we lay this out in memory, what ends up happening is every time, so it's always going to be aligned towards your well, the memory that you've chosen. So if it's on DCD, it'll be on a 4-byte boundary. That just means your memory address is divisible by 4. All right. And about that, there's also one more thing I want to talk about, which is the endianness. So let's go down. So endianness is essentially how the direction in which we store data. So we have big endian, and then we have little endian. Right? So the difference between these two is the order in which we store a byte, or like a word. Let's say, for example, we had this word, right? We had 2x, 1, 2, 3, 4, 5, 6, 7, 8. Right? In big endian, what it means is that the end byte or the end byte is stored in the big in the larger memory address. So let's say, for example, we had this is our memory. Right? So in big endian, what this would look like is so the little byte, the end goes on the largest memory address. So this would 78 would go here. Then we had 5, 6, 3, 4, and then 1, 2. So this is what it would look like inside a big endian representation. Now little endian is the opposite. The last byte goes onto the little memory address, the smallest memory address. So what's the last byte here? 7, 8. And what's the smallest one we can fit? 0, 0. So what this would look like is 7, 8, 5, 6, 3, 4, 1, 2. Cool. Yeah. So that's the difference between big and little endian. And in ARM, or at least in this course, we mainly focus on using little endian. So if a question asks you to draw like a memory layout, you can assume that the question is assuming little endian. So let's just go through this example. So we have this data section here, right? So assuming little endian, let's try to draw it out. So we have this word here. So what this is this is essentially, well, 0xbef. Since it's a whole word, what we're actually looking at is this. Okay, I've got good handwriting, right? So because we're not using the whole word, we actually have to pad um, the leading digits with zeros. So this is what this first DCD would look like. So let's put that into memory. So remember, little endian, which means the the end part goes into the smallest address. So what's the end part here? We have EF. That's our first byte, right? So we will have EF here. Then we would have BE, and then we have our 2 bytes of zeros. Yep, and that's what beef would look like inside your memory. Now the next one is DCB 67, right? Actually, this was not intentional. Uh, so DCB 67, what that does is that's 1 byte only, and since it's just 1 byte, NDNS doesn't really matter too much. So we can just put the 1 byte here. Oops. So we have 0x67 there. Now, the next step is this align function there. What does align do? So align sort of it's self-explanatory. It aligns with the given with the given boundary with an offset. So it would look something like this. Let's say we had align like A, B, right? What that does, it aligns it with it finds an address that's divisible by A, and then offsets by B. And the thing about A is that A must be a power of 2. So it can't be like 3 or 7. It must be 2, 4, 8, 16, etc. So let's look at this example. Oh, this is wrong. This should be oops. This should be 4, 3. Yep. Yeah. So there's slight typo there. So align should be 4, 3. So what this does, it finds the next available address that's on well, the next available address is offsetted by 3. So what's an available what's a valid address here? So first of all, align by 4 means we want to have addresses that are divisible by 4. So this could be this one, this one, this one, and right now. But then we also have the offset of 3. So what this means that is we want to offset all of these options by 3. So let's say let's use green. So for example, this first one, this could be a valid address. This one could be a valid address, and this one could be a valid address. Because as you see, I've offset it 1, 2. We've offset it by 3 address spaces, right? So that means if we look at this, the next available possible address we can use is actually this one, 0x47. So what that means is it just fills up zeros until we reach the aligned boundary, right? And then after that we have our DCB, which is 0x12, and we can put that in there. And that is what memory layout looks like. Any questions so far on this? Anything on chat? No. Cool. Uh, let's see. How much time do we have? I want to do a couple questions. All right. Let's just look at this first. So store and load. There's this is also pretty important. There's definitely going to be questions on loading and storing. So first first up, you guys know how to load, right? It's we have your LDR, then the register you want to load to, and then like some address, right? Now, we also have various alternatives. We have LDRB, which is to load a byte, and we also have LDR. Oops. So yeah, hold on. Yeah. So we have. Oh yeah, you can just use LDRB for now. So sorry, these two are the most important ones. So an LDR loads in a full word by default. All right. Now, there's a couple ways of doing indexing. So when you want to load like multiple things, we can use three different type of indexes. We have pre-indexed with the write back, and post-indexed. So what do these mean? Let's look at this code snippet here. So pre-indexed, what it basically means is we have um, our load, and then we have our address. Well, let's just use R1. We have our address here, and then we have some sort of offset. So what this does is it adds on the offset first and then loads it in. So if you want to think about it in like C code, let's say we had a pointer. You guys are familiar with pointers, right? In C? All right. So let's say I had a pointer, right? What that does is it increments it by the offset first, and then it loads it in. So it will look something like this in, if you want to think of it like as a C type C type pseudocode version. So it just adds on the offset and then loads. Now, pre-index with the write back, what this means is it will put the result back into the original address register. So the way we do that is by giving, I can write, an exclamation mark. So this exclamation mark means put the result back into the register. So what does that mean? It means something like this. If going back to our pointer example, if we're at x, we would do x is equal, we would do something like x plus equals offset, and then we would load x. So notice how this one, how in this top one here, we didn't actually store the result. We just put it straight into a load function. Whereas here, we put x back, we put the offset back into x, and then we load it in. So the value of the address changes, right? Whereas without write back, we don't change the address. And then we have post indexed, which is essentially, which looks like this. And then we just put our offset outside the square brackets. Right? So what does that do? If we look at our weird pseudocode, we actually reverse the order. So we load x first, and then we increment by the offset. Cool. Let's see, do we have time? All right. So these were the various variants of loaded store. So obviously we had by default, these were words. This stores a byte. This stores a half word. And same thing here. But now LDR SB and LDR SH. What does that mean? This came up in one of the previous exams. S. So S actually stands for signed. All right. So when we load, it actually considers the sign of the value. Now, can you think as to why that might be important? Like, isn't the value just the same? Yep. Yep, exactly. So just for the online recording, um, what he said was, um, our registers are 32-bit long, right? But with bytes, the signed bit will be in the 8th bit. So let's say, so signed bit is the 8th bit, right? Whereas in a register, it's 32-bit. So what ends up happening is when you use SB or SH, it actually pads the missing bits with your sign. So let's say, for example, we loaded in this byte here. All right. So as you can see, this is a negative number. How? How do I know that? Because the first bit is a 1. So if we load that into a register, what if we used LDRB, oops, if we use LDRB, what ends up happening is that it just ends up filling up the rest of these with zeros. And then we sort of lose the meaning of our sign. Now, if we use LDRS, what that does, it looks at this bit and then it copies it and it just pads it. Oops, where did I go? It pads it with signs. Well, the sign of that bit. So in this case, it would fill up with a bunch of ones, and that would be like the 2's complement version of that negative number in a word compared to a byte. Cool. Then we also had a literal pool. Just for the sake of time, literal pool is basically a section of code which stores your data values. So let's say we have you have your like DCD here. Oh, not even DCD. Let's say for example we have um, we see the LDR R0 and we have something like, I don't know, num, right? That this value of num would be stored inside the literal pool, and that could be defined like so. Um, so yeah, literal pool is where all your constants are stored, and the location of your literal pool matters because with a load instruction, we only have, well, how much was it? 12 bits to work with, which means we only should be around 4 kilobytes worth of um, range that we can go either way, like negative or positive, to reach this literal pool, right? So um, this has like a maximum range. Now, there is a directive called LTORG, which basically tells the assembler, make the literal pool here, right? Now, this is useful because let's say you had a big program, you probably want to place your literal pool in a place that's accessible by like the things that are going to use it. So if by default you put it at the end and you have a massive program, well, your instructions aren't going to be able to reach that literal pool if it exists outside of the range. So we can use this assembler function here, LTORG, literal pool origin, to like tell the assembler build it here instead of by default at the end. Cool. And let's see, and what else do I want to talk about? Well, let's just quickly go through this. This also comes up pretty often. Polling. So, what is polling? Polling is essentially, um, in other words, it's sort of like to keep looking at different things, or like to go around checking the status of different objectives to see if they're done or not. Let's say, for example, we had like 3 tasks, right? Let's say we had like a task 1, task 2, task 3. What polling does, it says, okay, let's look at task 1. How are you doing? Are you done? If it's not done, I can move on. Let's look at task 2. Is task 2 done? If it's not done, we can move on. Oops. And then we can go to task 3, check if it's done or not. So we sort of like just go between like each task to see if it's done or not. I think it's looking at each task takes a certain amount of clock cycles. There are hold on. So there are like disadvantages to this. So for example, let's say for example this is a hard disk. For example, this is a disk, right? And that's like reading data like pretty often. You might spend a long time like pulling on this task, which means you're wasting CPU time doing something that could be like doing something else, which is why we have an alternative, which is called interrupts. So with interrupts, all you need to know about interrupts is that instead of like checking each like status or each task, the task will come to the processor itself. So let's go back to this example like of 3 tasks, right? Let's say for example, task 1. So instead of going through uh, each task and checking it, the task will say like, oh, it would give like a flag saying, hey, I'm done. Please take a look at me. I need some help. And then the CP would like branch over there to see like, okay, what do you need help with, right? So it's you can sort of think of it as instead of like an examiner walking around checking each like paper one by one, like a student could just like raise their hand and then the examiner would like come to them. That's like one analogy um, you could think of. Yeah, I think that's all you really need to know about polling versus interrupts in a nutshell. I did want to I go a bit over time. I did want to go through a couple of past exam questions. Do you guys want to take a break first, or do you want to go straight into an exam question? Any preferences? Break? Let's take a quick break first. Um, yes, it's 10 minutes before 3. Do we have? All right. All right. We can take like a 5-minute break, or 5 to 10 minute break, uh, while we reconvene. I got it. Sure. So I can basically, um, So the question like what is like this object? Yeah. Okay. So this could be like anything. So some big examples could be let's say for example you have a keyboard. Okay. So what could a keyboard do? If one uses intros, could be like key press. Like someone presses the space bar, that could be an intro. Like oh say press space bar. Otherwise, if you just it will be like hey did anyone press any buttons yet? No, did anyone press any buttons? So like you keep checking like if you anything going on. So that's just like another one could be say like a hard drive, right? So a hard drive is let's say for example when you're writing like to your memory, like it needs to keep like updating, right? So for example you can say oh I'm moving this from your RAM to my because sorry let me tell you it's like you wanna move stuff from the RAM to your hard drive, but that takes time, right? Obviously. It's not easy. So what it's like I'm going to start the hard drive and then sort of say like oh I need like the next part of general stuff. Let's say like it's like our memory, okay? And it's like divided into like different chunks. So what happens first is I grab this first one. So I send this first chunk to the hard drive. Everything that goes into the hard drive. And this takes time, right? So this one takes time. So the intro will be like, are you done? So the will be like, are you done completing this one so I can give you the next one? So this will be like the second one. Because once this one is done, I can take the next one. And once the second one is done, I can take the third one, and so on and so forth. All the parents were yeah. Yeah, so instead of going like, oh, hey, I do this, you can, it will be say, oh, I'm done with this. But obviously, you also have like your main program, right? Like whatever your main thing is, also like the main function. That also you also need to do that. So it's sort of like your CPU has to split between the main function and the main function component. So that's to like switch back and forth really fast. Yeah. That makes sense. Yeah. So we have this, but I think was yeah, that's not really necessary because it's more accessible in the lab than it is in the most important part of it is sure. Yeah, the most important part. Like, and then it was just everything that's in the slides will be but for the other weeks, you need to know in general what is like what is GPI. So you remember like your you have your inverter, your set and gear. You have those. Yeah. So you just have to know like they exist. You don't really know too much about them because they don't really assess you like deeply. More of how you write code. So this exam, it's I would say maybe like 40% theory and like 60% of coding. Yeah. So coding it with handwriting code. Yeah. But I think from my experience, there's like maybe like two or three like coding questions. But usually it's like two small coding questions, and then the last one is usually like a long question. So as long as like you're comfortable like writing assembly, like you can practice like on but then afterwards like you have to like realize like it's practice like without using like an IDE. So like for example, I would use say like text editor because that one you don't have like all the things to help you. So like it's almost as if you're writing on like paper. Yeah. I mean, like, Oh, let's see. If we can. All right, guys. Oh, I will. If you guys have any like questions you want me to go through, like from the past, like from the sample exam, you can feel free to ask. Otherwise, I've selected two questions that I think I'm going to go through. I'm going to prioritize. Oh, I've frozen the screen. Oh, okay, that's a. All right. Um, yeah. So in the exam, in my experience, there's a large portion of it which is focused on coding. Um, well, let's zoom in. All right. So the the theory part, oh, that's all cool and all, but yeah, a lot of it will come from a lot of the marks are related to how you can program, and the programming unfortunately is going to be handwritten, which is pretty funny. Uh, it's back to old school comp sci exams. Um, yeah. So for the sake of time, I think I'll prioritize these two questions. Yeah, I'll prioritize these two questions, and because I think this is most like it's the most indicative of what you might expect in the exam. All right, so let me. All right, let's do this first question. So let's let's look at the C code here. We are given three numbers, A, B, and D. All right. So first, the C code is asking if A is bigger than B, or bigger than or equal to B, then D is equal to A plus B. Otherwise, D is A minus B. And we've got two variations of this question. We have if A, B, and D are 32 bits, so that they fit into one register. And the other one is if they're 64-bit. Let's do this one first. So 32-bit register. Let me pull this up. Let's go. All right. Oh, that's not good. You guys can see the very scuffed setup. Cool. So let's look at so we have if, let's just copy this into, so this is the program that we want to build. So first off, we want to check if hold on, let me just give me a second real quick. Sorry about this, guys. Okay. Hopefully this is working. Yep. Nice. All right. So first off, let's see if I can zoom in. Is that big enough? Can everyone see this? Cool. So first off, as the thing that we can immediately see is that we have some sort of comparison, right? And let's just suppose we have, say, R0 is A, R1 is B, and see, R2 is D, right? So that's, it's defined. Use this as our definitions. Usually, they will give you the definitions of where each variable is stored, but if not, you can make an assumption, but you have to always state your assumptions. Right. So first task is we need to compare. So first of all, what is this? We have to compare A and B. So let's do that. Let's do main, and let's just do CMP R0 with R1. So that compares A and B. Now we want to check, is A greater than or equal to B, right? How can we do this? If you remember, this is a bit of a scuffed setup because I don't have the data sheet like on. This is not what I intended. But if you had the data sheet on up, you would notice in the bottom left of your data sheet, there is like a table showing all the possible different comparisons. And so we can actually just choose the most relevant one. So in our case, we want to check if it's bigger than or equal to so if A is greater than or equal to B. So we can do something like what is that? That is greater than or equal to GE. So we want to use GE somewhere. Now there's a couple of different ways we can do this. We could do another label, so you can go bigger than, or you can just go bigger. And we can do something like if it's bigger or equal to, we can just do BGE, bigger. Right? And then here we can do, if R2 is D, then we just do our add R2, R0, R1. Right? And then if it's not bigger, then we can do what's it, we can subtract R0 and R1. and then we can go, let's just say we had any of an end, right? And then we just, after we're done, we branch to the end. All right. Does everyone understand what I've done there so far? Are there any questions or anything that's unclear? Yep. Yes, you do get the data sheet. So it's if you remember your appendix, there was like a bunch of there was a table of all the instructions. Yeah, the lab manual. You get the exact same thing. If you open up your sample exam on Moodle, I think you'll see there is a data sheet at the very end as well. That's the same thing as what you would get. All right. Cool. So far this is all right, right? But let's suppose the question asks us to implement the most like optimal way of doing it. Do you think this is optimal? Anyone take a guess? Yep. There is a better way of doing this. As you can see, lots of branching. And as we said before, branching is not good. We want to try to avoid branching where we can. And how do we avoid using branching? We can use our conditions, right? So if we actually look here at our bigger um, function or our bigger branch there, we're only really doing one instruction, right? So what we could do is instead of branching to a label and then just doing one instruction, we can actually combine the instruction and the condition at the same time. So you can do something like add GE, R2, R0, R1. And then we can get rid of this. All right, cool. So now we've completely gotten. Oh, what is that? Oh, I don't know. So we've completely got rid of the branch. Now we've got an optimal code now. So is everyone happy so far? So yeah, you guys think this code is correct now? Yeah. So for the recording, what someone said was this statement here is always being executed, which, well, that's not what we wanted, right? So you have to be careful. We also need to add a condition here to make sure this statement isn't executed. It only executes if um, this one doesn't. So what we can do is just find the opposite of the opposite condition of GE. So what's the opposite of GE? Greater than or equal to? Like exactly, less than. So we add a less than condition there, and now we should have a working. Yeah, this should be a working solution. Cool. And yeah, again for reference, I know off the top of my head, LT is less than, but you don't have to memorize it. It will be given in the data sheet. So you just have to look at there and say, oh, I need a less than comparison. Um, let's look through the data sheet and see what letters I need. Cool. Let's look at the next stage, which is 64-bit integers. Now, this one's a little bit trickier. So let's suppose, just for definition's sake, we have our, let's see, we have A is equal to uh, R, say R0 and R1. Oops. Let's say B is equal to R2 and R3. And let's say D is equal to R4 and R5. So in other words, what this means is because these are 64-bit integers, and our registers are only 32 bits long, we need two registers to store a 64-bit number. And this is sort of just like a construct that we can define ourselves. All right. So we can choose any two registers and combine them together in our heads to sort of um, form a 64-bit number. So in our case, we can say like R1 is like the lower 64 bits of A, whereas R0 is the higher, or the more significant bits of A. Right? So using this definition, let's now try to code up the C code, or the assembly code. So this one's a little bit more involved, because now we're sort of involving two sets of registers. So let's think about it. Let's okay. So what were our definitions? A was R0, R1. B was R2, R3. And D was it R4, R5. Now, if we want to check if A is bigger than B, what do we need to do? How would we do it if we had 64-bit registers? What would your approach be? Anyone want to take a guess? Yep. Exactly. So what was said was we want to compare the more significant bits. So that would be R2 and R0 and R2. If they're equal, then we'll only then do we compare the less significant bits. Sorry. So how would that look like? Let's make our main function again. So let's compare R0 and R2. If they're equal, oh hold on, let's do this. Let's say let's just go to let's just say less than. Right. So if they're equal, so if R0 is bigger than R2, then what am I doing? Compare again. Then we want to, let's just say we branch. Let's just do BLT. We branch to less than. So then we do this. We do our subtraction code here. We'll put that in later. So that's if the first two, all the significant bits were not equal. But if they are equal, then we need to compare the least significant bits. How do we do that? We can do something like this. We can do CMP, CMP equals, let's see, R1 with R3. And then we branch. Now, hold on, let's also mark, yeah. Okay. Does everyone see like the logic here? What I've done? So basically, what we do is we first compare the first two. Oh, this is all right. There you go. We first compare the more significant bits. If they're equal, then we compare the least significant bits. So then when we're on this instruction, the flags that hold the comparison depend on what was the last instruction that was run. If that makes sense. So if these were not equal, if the most significant bits were not equal, then the flags represent the comparison between R0 and R2. And if they're not equal, then this line, if it's working, this line doesn't run. In which case, the flags don't update, and the flags contain the comparison between R0 and R2. But if they were equal, then this line that I've highlighted will run. And then, oh yeah, the highlighted line will run. and it'll update the flags. So then the flags contain the comparison of R1 and R3. Does that make sense? Cool. So yeah, that's how we do the comparison between 64-bit numbers. Now we have to do the actual arithmetic. Now, how do we add two 64 bits number together? How do we do this? And I want to, yeah, exactly. So let's add the least significant bits together. So that would be add let's see, R1 and R3. But where do we put this? Where do we put the result? Yep, I heard someone say R5. We put in R5, the least significant bits of our result. Easy. Now, this is cool, but we need to get the carry bit. How do we get the carry bit? Exactly. Someone said add s. So remember the s instruction, or the s suffix updates your flags. So when this instruction is run, if there is a carry bit, we now have access to it. Oh, what is up with the screen? Cool. Now, how do we actually add the carry bit? This is, if you look at the data sheet, which we don't have, unfortunately, there's actually an instruction called ADC. Now, what does ADC do? ADC just means we add and we also include the carry bit. So it looks at the flags and sees, oh, we have a carry bit. Let's add that on as well. So we then do the more significant figures, do R4, was it R0 and R1. And what this does is it takes the carry bit from the previous instruction and also includes it in the next addition. Cool. Oh yeah, my bad. R2. You're right. Cool. And let's just say we have an end here. And we can like branch to the end. Cool. Now for subtraction, we can do a similar thing. So we can do sub. What am I writing here? Sorry. SBC. Yeah, you would be correct. I would eventually write SBC, but we should probably do the first instruction first. So what would I write in this first instruction? Sub S. And then what am I writing here? R1, the R5, R1, R3. Yep, exactly. We just copy over what we've done on addition, and again we can do the same thing with sub SC. So just as a pointer, so SBC, what that does is it's the same thing as ADC. It subtracts if with the carry. So if the previous result had to borrow, because remember the concept of borrowing, right, from subtraction. If the previous subtraction had to borrow a digit, then that digit is then subtracted from this, or that borrowed digit is then taken from this operation here. So and that ends up giving us the end result, and we can just do b end. Yep, and that should be yeah, that should be a working program. Yep. Everyone happy so far? Any questions at all? Yep. Usually, yep. So the question was, would we get marked down for writing inefficient code? If the question explicitly says you must write optimal code, then yes. Usually when it says that, it means try avoiding like branches or like, um, unnecessary lines of code that might not be, that could be compressed down, right? Um, if it doesn't say, you might not be marked down, but if you write like really terrible code, like say for example, I for some reason did like, add R0, R0, R0 for whatever reason, like now it's just, I'm just wasting clock cycles. Um, oh, no, that's probably, maybe not, let's say move. Now I'm just like randomly wasting clock cycles, right? Um, then you might be like marked down. But usually the questions will explicitly say whether or not to write optimal code. Cool. Yeah. Any other questions? Yes. Um, I'd say this one might be worth. Okay, this one might be worth say like 8 to 10 marks, whereas this one, the 32-bit one, I'd say would be worth like half of that, like 4 to 5 marks. Yeah. So with like sub questions like these, obviously the more complex it is, it will be worth more marks. Um, again, that's just like a estimate. I can't tell you for sure what David might give you, but yeah. Sorry. Um, how much is? Oh, I forget how much the. Uh, then I believe it should be around there. Okay, maybe around exams worth 30 marks. I say this one probably be around like the 6 mark area then, because a large portion will be due to coding, and this is a relatively, I'd say it's a medium-sized program for this task. Cool. Let's move on. There's one other question I want to do before uh, wrapping it up. Uh, was this one. All right. So this one isn't, well, this one, you don't have to code anything, but this is more of understanding the code. So usually for stuff like this, there are a couple steps I would take. First of all, let's look at the question. Question is, what does the program do? And there's also like sub questions asking like, what's the contents like afterwards. But anyway, we first look at this program, right? Let's move over to my code. Yep. All right. So here's the program. So it's kind of overwhelming if you just look at it like straight on. So what I like to do for these questions is sort of break it down into different parts and try write like a C or like pseudocode type, like try to convert it to C or pseudocode to sort of just get like a better idea of what's going on. All right. So let's break it down then. So this first part, we have a main function. And what are we doing here? We're taking the address of some array. So I can immediately tell we're dealing with an array here, just from like the names of the variables. And then we're branching and linking to a function. So if you guys remember AAPCS and functions, we have like a labeled function here. Let's move this like that so it's a bit easier to see. So it looks like as if we're calling a function. So if I were to write some C code here, let's see. How do I want to do this? Let's do Q4. All right, and right. Oh, this is terrible. You guys can see this, right? Nice. All right. So we have some main function. So I'm just going to try convert it. And then I can see immediately we have some function here, right? So we have some funct that we're defining. And it looks as if it returns an R0. So this thing does return something. I'm just gonna assume int. Oh, oops. So it's a function that returns something. Now, if you remember APCS, how do we pass arguments into a function? Do you guys recall? Yep, A0 to A3. Oh, A1 to A4, which correspond to R0 to R3. And if you look here, before we call the function, we're putting two values into R0 and R1, which is, this could be translated to A1 and A2, right? Oops. So what does this look like? We're passing the address of array A, and we're passing in the number 7. So let's just say we have like some array. Well, how do you do arrays in C? Something like that, right? Let's just assume this is filled, right? So it looks like we're passing in like a point, the address of the array, and then it looks like we're passing in the number 7. So it looks like, array, something like that. That looks like what the function is doing, right? Everyone can see that? Cool. Now let's look at the function. What are we doing here? So we have this line. What does that line do? That's just creating, well, the stack frame. Because you remember in APCS, if we're using if you're using the V variables or the V registers, that would be R4 to R8, I believe. Oh wait, no, R12. Um, we want to store them in the stack frame. And as you can see here, we're storing R5 and 6. But yeah, that doesn't really help us with what's going on. Let's see what now. We're storing a variable into, we're storing 0 into a variable. So let's just call it like R5 equals 0. All right. Oops. And then after that, it looks like we have something called a loop. Oh, a loop. Nice. Um, just looking at the labels, I can probably tell we're going to have some sort of loop here. So I'm just going to leave it as something like that. In fact, I'm going to do something called a do loop. Now, let's look what happens next. We are loading in R0 and 4. What is R6? So we're doing something like R6, and we're loading in the value of what's R0. R0 was the array, right? So it looks like we're loading in the value of the array plus 4. So the address plus 4. And do you guys remember what happens when we plus 4 to an address? We just shift. Yep. Now, there's a slight problem with this one, with the translation. This is actually post-indexing. So actually, what's going on is we set it to the value of array, and then we advance. Oops. Oh my god, I can do things. We advance the pointer by 4, right? So what does that mean? We're just sort of like incrementing the pointer, or like incrementing the sorry, we're incrementing the index of the array, and then we compare R5 to R6. So what's R6? R6 was the value of the array. So let's just do that. So is R5 equal to R6? And if it is, so BCS, so that means well, that's actually looking at from top of my head. It is just uh yeah, it is just checking if it's larger than. So that's an unsigned comparison. And if it is, then we branch to small. So what does small do? It subtracts. Yep. So hold on. Oh, yeah, sorry. Yep. Hold on. Wait. Oh, I see that. I see why. There we go. Um, so if it's small, then we just subtract num minus, so minus equals 1, and then otherwise we, hold on, what am I doing here? Otherwise we set um, R5 is equal to R6. Sorry, I'm just getting a bit lost here, but yep. So do you guys see? Do you guys see how I've managed to like compile that so far? You want me to zoom in? Hold on. Is that? Hold on. Let's see if I can make this clearer. All good. Nice. Um, yeah. So that pretty much sums it up. Yep. Now, what happens here is, oh, and then yeah, all right. And then at the end, we're actually after the loop exits, we're actually we actually find we actually move R5 to R0. So that means what does R0 mean when we're in APCS? It's also the return value. So this line on line 28 actually means return R5. Now, looking at this C code, it's still kind of complicated, right? And it's still sort of hard to see what exactly is going on here. Now, what is? Oh, hold on, I'm missing one important thing. Um, we this the while loop has a BCS thing. So all it's saying is we're comparing the value of R1 to 1 and just checking if that is positive. And what was R1? R1 was num, correct? Oh, I probably should define this. It's num, and then R0 was array. So what it's saying is num bigger than 0? Is it positive? All right. Now we can actually sort of condense this even more. So what this is actually doing is saying like is hold on, let's see if I can do this. Okay, so R5, let's look at this if statement real quick. This is sort of messy. We can actually reverse this and say hold on. No, this is should be like this, my bad. I've messed this up. Yep, okay. So this if statement is bit reversed. So let's try move this into like this. And oops. Oh, did I get it right the wrong way around? Hold on. Let me take a look at my notes. Yeah. Okay. Now, so R6 is we can say like R6 is set to array. So we can sort of say like num, like current number, right? Because we're looking at the current number in the array. So we can do something like that. And then we advance the pointer of array by 4, right? And in C, we can actually just compress this into something like that. And that should work, sorry. And then what we have next is, well, this num can, we can just move this over here just to make it clear. And I think that should look a bit better. Um, yeah. Now looking at this, I think we can sort of, it's a bit clearer now, I think, that it's uh, written this way. So if you look at this function, we're looping over the array. If R5 is, sorry, no, it is the wrong way around. Sorry. If R5 is less than current num, then we set it to current num. Now what does that tell you? R5 is always, must be always bigger. We're actually looking for largest. So we can actually set this, change the name to be R5, and suddenly this function looks a lot more readable, right? And if we look at this, what does this function do? Can anyone tell me? Yeah, exactly. That's all it does. It just sets, it just finds you the largest number in that array. Um, and yeah, sorry, I'm just double checking. Yeah. Oh yeah, my bad. It is supposed to be. Um, yeah, you can do like plus equals 4. Yeah. Uh, I'm not sure if that's probably not correct C syntax. But you get the general idea, right? I haven't written C in a while. Oh, C like this in a while. Yeah, so that's the sort of gist of what this program does. And yeah, to answer that question, originally, all it does is find the largest number. Um, so yeah, I just wanted to go through like the strategy onto how to sort of decompile an assembly instruction for you to understand. You sort of go through each block of the assembly. So how we did before was went through each block and then looked at how looked at what it was doing, and we sort of just like write very vague C code first, and then after that we can take a close look at to how each variable is interacting with each other, and then we can sort of refine the C code into something that we can understand. Um, and in fact, this this question isn't complete yet. There is this last um, this last part here which we didn't use. We can just say like int results is equal to that, just so we can store it. And all that did was it, because we moved so we moved the result to R2. So if you want, you can say like this is R2. Then we take the something like that again. Um, so you find the address of array, and then we set the 28th index to be R2. What is the 28th index? What does that mean? Yeah, exactly. All I did was um, so and I can like clean this up again. I can change the result, and all I did was set the seventh array or the seventh element to be the largest element. Um, yeah. See anything else? Yeah, that looks good. And that's all. That's pretty much um it for this question. I think there was also um a part two to this question where we sort of step through each like clock cycle and label each register. But unfortunately, for the sake of time, I don't think I have time to go through this. Sorry about that. Does anyone else have any questions or anything you want me to clarify about the course? Yes. Yep. Yeah. So yeah, the question was, will we ever have to write like convert assembly to C? The answer I would say is no. Um, although I can't guarantee it, but I'm 99% certain that you won't have to write any C. Um, and if there is C, it's mainly up. I guess it's the C that you would write in the exam is mainly meant for like your own understanding rather than for it to be marked. It's like it's meant for your working out, is what I want to say. Yeah. Any other questions? Yep. Um. Okay. The question was how often will be assessed on the second half of course. So stuff about the exceptions and interrupts. Um. It's mainly theory based, so you won't have to write any code based off exceptions or interrupts. Um. You have to understand. You just have to know the theory behind it. There might be like a couple like short answer questions. And that could be like why might you prefer like interrupts over polling? Like um what's a so a disadvantage of polling, for example. There might be a bit of there might be some calculation questions based off polling. So it might say like a CPU cycle spends say like 100. So the CPU spends 100 cycles doing an interrupt on this device. What percentage of um, CPU is spent doing interrupts? You might get a question something like that. If you looked at the past papers, I think there might have been one of those questions in there. Yep. Um, yeah, I'd say like yeah, most it's theory based. Most of I said a good chunk of the marks would be to do with um, programming and especially ARM. Yep. Any other questions? Yes. So is your question like how com Yes, I would say it's probably similar to the lab exercise. So stuff you would have done in lab 2.1 and 2.2. So if you remember like your was it like a max of 6 or your what else? I can't remember off the top of my head. Like your string to upper. That sort of level is what you probably expect to do. Um although I would say with the coding questions, there's a couple like short code answers you have to give. But usually like the last question is like it's like a longer, well, it's a larger coding problem. So you'd have to uh so you have to define like your main functions, whatever other functions you define. So it would look something similar to this. So you have to write a whole program for the last question, usually. Any other questions? Okay, anything else on online? Um, what was the question for that example just then? Um, for which one? Oh, well, the question was, someone asked, basically, how similar is the code in the exam going to be to like the lab questions compared, or is it going to be similar to lab questions or similar to the lecture questions, or like this? Yes, um, it will be similar to those ones as well. Yeah. So I would say because I say the lab questions like from week one and sorry lab 1 and 2, so 2.1 and 2.2, and the weekly exercises are about the same same difficulty. So you'd expect like those sort of style of questions. That makes sense. Cool. If there's any other no more questions, yeah. If you had any more questions, you can go ahead and like message me. Um, you can message me on Teams. That's my name. Um, and yeah, thank you guys for coming. Sorry it was a lot of overtime. Thank you. See ya. Oh, so someone's asked. I can just quickly answer it if they're still watching. Someone's asking if we're supposed to use the LCD and the LED ladder at the same time because they use the same pin. Um, what you can do, um, there's sort of two ways you can approach it. One is you don't have to have the LCD on all the time. So if, for example, you want to use the ladder like when you're like sleeping or something, so then you can turn off the LCD and then use the ladder. Otherwise, what you could do as well is sort of switch back and forth between the ladder. Like you turn off the ladder, switch on the LED, then switch off the LED and turn on the ladder, and switch back and forth really fast. But you might see like you might get like a some weird artifacts if you do that. So my best advice would be turn off the LED if you're not using it, and then use the ladder while the LED is so the LCD is off. Cool. Otherwise, thank you so much, everyone.